Welcome back. This is part 3 of Enzyme Mechanisms. In this particular case, we want to look at a particular example, which is the chymotrypsin mechanism. Remembering that the last time we talked about the ways in which enzymes produce the rate of reaction. We talked about acid-base catalysis, covalent catalysis, intermediate formation, auxiliary effect, transition state stabilization. So what we want to do is to look at these things in action. What we're going to do is look at the enzyme chymotrypsin. Remember, this is the enzyme that feeds on the carboxyl side of the aromatic amino acids, tyrosine and tryptophan, primarily. Things that have line on. Why are we going to look at this? Well, there's a lot of different mechanisms we can look at, but this is particularly nice because it involves all 5 of these mechanisms within the same overall mechanism itself. So it makes a good way of looking at it. Plus the fact that there's a series of protein enzymes, which are called serine proteases, and these all share the same kind of mechanism. So we're not just looking at chymotrypsin, we're actually looking at other enzymes as well by examining these particular mechanisms. So what do we know? Well, if we add diisopropyl phosphate, it makes the enzyme inactive. This molecule was one of the typical kinds of gases that were used in chemical warfare during World War II. And so after the war, the entomologists wanted to find out why it is so effective in terms of unfortunately killing people. And what they found is that this molecule is capable of reacting with serine residues on enzymes. However, if you mix this molecule with serine by itself, no reaction occurs. And in fact, if you look at chymotrypsin, which is treated with this molecule, you will see that there's only one serine of all the possible serines that are reactions. So there has to be something, a special serine that involves causing the reactivity. Then we have phenylalanine or ketone, and this reacts with histidine. When it does this, again, the enzyme becomes inactive. So we've identified 2 amino acids, serine and histidine, which apparently are critical for the enzyme reaction. So we know the chemistry. And you must realize this was being done in the 40s and 50s, at which time we do not have all the genetic mutational capability that we have today. Now we simply would do site correcting and genesis, and this way we could test each amino acid and find out which is important. Back then, all we had was our chemistry. So the mechanism, the proposal, involves the serine and the histidine and the aspartic acid. Now remember, histidine has this unusual property of having 2 nitrogens, and protons can be on either side, depending on the situation. Aspartic acid at pH 7, of course, is going to be negatively charged. Serine, which has a pK way up there, on the order of 15 to 16, that's what you find. So that's going to be basically neutral. So what happens? You have a negative charge on aspartic acid. This negative charge is going to start attracting the proton on the histidine. Now, if the proton left the histidine, then that nitrogen would become negative. Nitrogens do not like to be negative. Positive, neutral, but not negative. So what happens as the aspartic acid pulls on this proton, trying to pull it away, the other nitrogen, the histidine, then turns to serine and starts pulling on that proton. The net result is we have a slow transfer of protons in this direction. But in the opposite direction, you have a negative charge here because it's partially neutralized. Goes to histidine. Now the histidine cannot be negative, so it pulls on the serine. So the negativity, if you will, negative charges will disappear on this side and appear on the serine. So this oxygen now is going to have an excess of higher electron density. and therefore can become a very powerful nucleic substance. Again, this is proposed. The X-ray structure would indicate that these are not close, but now we're dealing in the range of mechanisms. Mechanisms and enzyme methodology can never be proved. All we can do is disprove it. So until you knock it down and say this can't happen, this still is a possibility. Now let's take a look at substrate binding. Okay, in the textbook it shows the sort of a valley or crevice into which the R side ring can penetrate. In chymotrypsin, this is a very hydrophobic and large opening. For trypsin, we go down the bottom, we see a negative charge. And when we remember the trypsin like positively charged amino acids. So now we understand why that might occur. And elastase, on the other hand, likes a very small amino acids. And so it has a pocket that is very, very shallow. So what we can do then is vary the substrate that we're going to react with simply by varying the substrate binding and still maintain the same mechanism. That's why what we look at. So we have three different enzymes all sharing the same kind of chemistry that's going on. So let's take a look at that chemistry. All right, this is going to be hard to see, so if you have a textbook, I really want to suggest